I'm going to continue on a topic that Sam just spoke very nicely about, exploring how we can constrain primordial physics through cosmological simulations, which is work I've been doing with a lot of people, primarily the ones who are listed here. I like to introduce this with this slide that sort of motivated my interest in this topic, which came from SNOMAS review now a few years ago, which compares on the left-hand side constraints from the CMB on these three amplitudes of three primordial bispectra that we're all familiar with: local, equilateral, and orthogonal. And here we show the current constraints and a range of forecast upcoming experiments. Maybe we should cross out S4. And on this panel, the similar thing, but for large-scale structure traces. So we have measurements from BOSS and a whole host of forecasts for upcoming surveys and some proposed missions. And I think what jumps out very clearly from this is that there is clearly a path forward to improve upon our current constraints by Planck in quite a significant manner. However, if we want to cross this theoretically interesting regime of FNL roughly order 1, modulo the discussion that Marco was leading yesterday, it seems that even with some things that would happen in sort of the next decade or so, we're still going to be far away from that. And so this got me thinking about what other ways can we possibly improve our constraining power. And one of them that jumps out is to go beyond the methods that are used here, which are the perturbative methods, and thinking about, can we use sort of information from more nonlinear regimes? And so this motivated, oh, sorry, this video is playing awfully. The work that my collaborators and I have been doing under this sort of name of the Quixote PNG group of basically simulating a broad range of types of primordial non-Gaussianity. This includes the standard ones, local, equilateral, orthogonal, but also other types such as primordial trispectral, or those that have extreme tail distributions, for example. And here's an example from one of our simulations where we have a Gaussian simulation on the left and FNL of 200 of the local type on this other panel. So all of our data here is publicly available, and we've now done a whole host of different analyses, and I'd like to just talk about one in a little bit more detail. And this relates to using these types of simulations to hopefully probe the symmetries of inflation. And probably all of you are immediately thinking about this, which is now quite a hot topic, which is the idea of exploring parity violation in the early universe. So as you're all aware, parity violation is considering the inversion of our coordinates here. And our work here is largely motivated by the work that Oliver, Zach, Jamin, and many others did, looking at parity violation in the BOSS survey, where they looked at 4-point functions of galaxies and compared the measurement of the 4-point function of galaxies of the left-hand orientation versus the right-hand orientation, and potentially found a difference between this. Now, I think there are some questions about the robustness of this measurement, but I think in general, it's still interesting to consider how we can possibly probe parity violation. And so to do this, we ran a suite of simulations that involved parity violation. So shown here on the top is a simulation with normal Gaussian initial conditions, and on the bottom case is a case where we added a large amount of parity violation in the form of a parity violating primordial trispectrum, and then ran a simulation. As you can see by eye, it's very difficult to tell any of the differences between these two simulations, even though this is actually a very large amount of parity violating primordial non-Gaussianity. So the work I'd like to talk very briefly about is being led by an excellent student at Cambridge, Yong Sheng, and he's been thinking about other ways of measuring parity violation. So the work that Oliver and Jamin have been doing is measuring the 4-point function. And that's motivated by the very simple fact that the 4-point function seems to be the sort of lowest order statistic that one would expect to see parity violation. And a simple way of seeing this is if we consider a bispectrum such as this one, this statistic is not sensitive to parity. And you can see this by visualizing the bispectrum as a triangle, considering what happens under a parity inversion. And you can see that this parity inverted triangle can simply be rotated back onto the original triangle. And this I think captures quite nicely why parity violation couldn't be probed by a simple bispectrum like this. However, that doesn't mean that you can't constrain parity violation with lower order statistics. And there's been recent work by many people in the audience here exploring how you can construct lower order statistics that are parity sensitive. And that's exactly the kind of thing we've been doing, but in this case, thinking about how this can be done in a bispectrum. And in this case, I think it's really nice to see that now if we consider a bispectrum that has a more complex shape, so for example, a bispectrum correlation between three-dimensional velocities and two matter fields here, in this case, you now sort of have a label on one of the legs, which has a direction. And so when you do the parity inversion and rotation trick, you find out that these two triangles will no longer line up with each other. The vector direction will be pointed opposite. And what this tells you is that if you can have something that studies a bispectrum between velocity and matter, for example, that would be a way of probing parity. And so what we've been working on at a very high level is to do this using a statistic that Manu introduced earlier today, which is the kinetic Sunyaev-Zavdovich effect, which gives a probe of the integrated line of sight velocity weighted by the gas density. So there's been a lot of work trying to measure this. And interestingly enough, detecting the KSC signal because of this line of sight velocity weighting is very difficult to do at the power spectrum level. So if you cross-correlated a map of the TSC with a galaxy over density map, this would be 0 on average because of this line of sight velocity could be positive or negative and cancels out. And so a lot of the community has worked very intensely on developing bispectrum estimators that probe this galaxy-galaxy KSC bispectrum. And there's been a flurry in the last sort of year or so of measurements actually applying pipelines to data and getting very high significance measurements of this bispectrum. And so the idea of this work has basically been to exploit all of this existing machinery and to use it to constrain parity violation. And so this is, I'd hope to have the final plot here, but it's not quite ready. But please come and chat with me if you're interested about the details of how we've done this and what we expect our sensitivity to be. With that, I'm going to change gears very slightly for the last sort of few minutes and talk about what are we thinking about next in this sort of framework of Quixote PNG. And really what I'm motivated by is taking what we've done so far, which has been in idealized boxes, looking at the distribution of dark matter only in a simple periodic box, to taking it more into the frame of observations. And so the idea here is now to go from this simplified scenario to create realistic maps of observables. And so this could be, for example, making light cones and studying the properties of the three-dimensional galaxy distribution or the integrated matter if you're interested in lensing. But I'm also very interested in exploring this in the kinds of CMB secondaries that Manu introduced perfectly this morning. So thinking about how these signals show up in integrated pressure or gas momentum. I'd like to just very quickly flash the slide. There's been a lot of talk about SBI for galaxy surveys in this workshop, but I'd like to say that actually I think SBI should be applied to CMB secondaries, which is maybe a little bit surprising, but the CMB secondary anisotropies, unlike the primary anisotropies, are highly non-Gaussian. In fact, to the extent that you can see this by eye, here's a map of basically the state of the art of our measurement of the integrated gas pressure through this TSC effect. And each one of these bright yellow objects that you can see by eye is a galaxy cluster that's detected at very high signal to noise. And there's about 10,000 galaxy clusters that you can detect like this. But if we were to measure the power spectrum of this, it's almost entirely noise dominated. And that captures how non-Gaussian this kind of field is. And the same applies to all of these other CMB secondary anisotropies. So to me, this motivates a campaign for thinking about how we can exploit that information, that non-Gaussian information, and it's motivating us to think about doing SBI in combination with galaxy surveys. So to underpin that, my collaborators and I are running an extensive suite of these simulations that contain mock observations of galaxies, lensing, and all of these CMB secondaries. So the TSC, KSC, CIB, lensing, all of these kinds of things. And the goal is to make a very large ensemble of simulations for these. So our goal is to make just over 1,000 of these simulations. This is a work in progress. So we have 150 simulations where 100 have been run at one cosmology and roughly 50 have been run where we vary one parameter up and above and below this. So these are useful for doing kind of like Fisher-like forecasts with these types of simulations. And in progress at the moment is a set of Latin hypercube simulations where we run and vary 5 different cosmological parameters over a broad range of parameters. And so these are designed for doing machine learning-based or simulation-based inference analyses of these types of fields. So we're about, this is a little out of date, we've done about 300 of these now, so we're about a third of the way through, and hope to finish in roughly the next 6 months or so, depending on how busy the cluster is. our approach here is to run, unfortunately, we're computationally limited. So whilst we'd like to run hydro simulations, that's not possible. So what we do is we run dark matter simulations. We construct light cones from these, and then we paint on top of these using a range of different methods, the observables of interest. So galaxies or gas pressure or gas density. I took these pictures actually quite a while ago from ChatGPT, as many of you can probably notice from things that are wrong with, for example, the hands and that. And I think that actually really captures our approach here. Because we're modeling dark matter and painting these things on, this is always going to be very approximate. And so our goal here is actually to include as many different painting methods as we can, so that there'll be a suite where you can test whether your pipeline depends on how you've chosen to paint on these observables. So for example, we have methods that use just the halo properties to paint on our observables, or methods that use the full field to paint things on. And so this will hopefully be a very useful suite for developing new ways of extracting non-Gaussian information from CMB secondaries. So I suspect I've probably gone over time, and I'll leave my conclusions here, and thank you very much for your attention. Yeah. Yeah, so we're running new simulations for this, and they are much higher resolution. So the original Quixote simulations, there were two. One was 512 cube particles, and the other was 1024 cube particles. The simulations here we're running for the Latin hypercube at 2,800 cubed. So they're much higher resolution, and the goal here was hopefully to be able to resolve halos that are of the mass where you could put in DESI-like galaxies. Hopefully, it's a bit borderline for that, but that's sort of our goal. Yeah, that's a very interesting question. Yeah, so if you just paint things on that they inherit the halo property, that would never show up. You need some additional weighting there. Yeah, I would be very happy if you have ideas on exploring that. I would be very interested to discuss that. We do store like local environment properties for each of our halos. So if that was a way of encoding that, that could be something we could add on. But yeah, that's something we haven't explored yet, but would be of great interest. Yeah. Yeah, in the context of this, not so much. So, but that is a very important question, and people are working obviously very intensely on that. I would view that sort of as the next step, right? I feel for CMB secondaries, we're sort of 10 or 15 years behind other communities. So for weak lensing community, people have been running these simulations and analyzing a whole host of higher order statistics. I don't know, peaks, minima, PDF, all of these kinds of things extensively, and that hasn't really been done for CMB secondaries, because we're in the regime at the moment where we basically have one simulation of these kinds of things. So our initial goal is to sort of assess whether this program is worthwhile. How much information would we get beyond the things that people are doing? And then if there is a lot of information, yeah, addressing those questions, which are pertinent for many other things, including the things you work on. Yeah, that would be the next step in my view.